All right, we'll start up this segment with Hess's Law, which I introduced briefly in the last segment, and hopefully when we get into a little more detail, it'll be a little more understandable for you. Um, and the reason that we care about Hess's Law is that the measuring the enthalpy change for a reaction is not an easy thing to do. Actually being able to conduct a reaction in a situation in which you can trap all of the heat being generated and measure it accurately requires, for most reactions, a fairly elaborate setup, especially if it's one that involves gases. But Hess's law makes things a lot easier because you can use Hess's law to calculate the enthalpy change for the reaction you're interested in from other reactions, from the enthalpy changes for other reactions. All you have to do is get those other reactions to add up to the reaction you're interested in. And you can do that by, say, multiplying all the coefficients by a certain factor in one of the reactions, or maybe reversing a reaction. If you can do whatever you have to do to get those reactions to add up to the reaction you're interested in, and you do the same thing to the delta H's for those reactions, like for instance, if you multiply all the coefficients in a reaction by 2, then you have to multiply the delta H by 2. If you reverse the reaction, then you have to change the sign on delta H. If you do all of that and you get those separate reactions to add up to the reaction you're interested in, then all you have to do is add up the delta H's, and they'll add up to the delta H for the reaction you're interested in. And so a little more formally, Hess's law says if a reaction can be written as the sum total of other reactions, then its enthalpy change is the sum total of the enthalpy changes of those other reactions. Or putting it a little more simply, if reaction A plus reaction B equals reaction C, then delta H for reaction A plus delta H for reaction B is equal to delta H for reaction C. And that's because delta H is a state function. That's why it works that way. So, for example, one way that you can create carbon dioxide is by burning graphite in oxygen. And that reaction would be carbon as 1 mole of carbon in the form of graphite plus 1 mole of O2 in the form of a gas yields 1 mole of carbon dioxide gas. And the delta H for that is negative 394 kilojoules. It's actually negative 393.5, but we went with 3 significant figures here to make it add up. Basically close enough. 3 significant figures. Anya, if you wanted to, now actually this is, of course, the standard enthalpy of formation for carbon dioxide, because that's what this reaction corresponds to. This is formation of carbon dioxide from its constituent elements in their lowest energy natural forms. You could also find that value for delta H by taking a couple of different reactions, like for instance, partially combusting carbon in the form of graphite in air to form carbon monoxide, and then taking the carbon monoxide and burning it, because carbon monoxide is flammable, in air to form carbon dioxide. And the enthalpy change for carbon plus oxygen forming carbon monoxide is negative 111 kilojoules. The enthalpy change for taking the carbon monoxide and burning it in air to form carbon dioxide is negative 283 kilojoules. And when you add those two things together, you get, what do you know, negative 394. And when you add the two reactions algebraically, dividing them at the arrow, so you add up, basically add up all the reactants and add up all of the products, you can see that you can cancel out things that appear on opposite sides, and you can add up if the same thing appears in more than one place on the same side, you can add them up. So you have a carbon monoxide on the right-hand side here in the first reaction, you have a carbon monoxide on the left-hand side in the second reaction, so they cancel with each other. In the first reaction, you have 1/2 O2 on the left-hand side, and in the second reaction, you have another 1/2 O2 on the reactant side. So you can add those up into 1 mole of O2, And what you end up with as the sum total of these two reactions is carbon in the form of graphite plus 1 mole of O2 yields 1 mole of carbon dioxide gas. So we've just by adding these two reactions together, we get the target reaction, the reaction we wanted, and therefore adding the delta H's for those two reactions will give us the delta H for the reaction we want. Okay, the book graphs this out sort of graphically on page figure 5.24 on page 265 or 275, depending on hard copy versus a PDF. Now it's important to remember that now in this case, we just took the two reactions as they were and added them together. So we didn't have to modify the delta H's in any way. But it's important to remember that if any changes are made to a reaction to get things to add up, then the delta H for that reaction has to also be changed in the same way. So if the reaction coefficients are multiplied by a factor, delta H has to be multiplied by that factor. So just as a quick example, carbon in the form of graphite plus O2, 1 mole of O2 yields 1 mole of CO2. Delta H for that reaction is negative 394 kilojoules. If you multiply the coefficients by 2, so that you have 2 moles of carbon in the form of graphite plus 2 moles of oxygen, yielding 2 moles of carbon dioxide gas, then the delta H for that reaction would be 2 times negative 394 kilojoules, or negative 788 kilojoules. Okay, and also you're allowed to reverse reactions in order to get them to add up the way you want. And if a reaction is reversed, that just means that the sign of delta H changes. The number stays the same, but the sign changes. And that makes sense because if you do the reaction in one direction and you get out a certain amount of energy, then it stands to reason that you would have to put in that same amount of energy to get it to go the other way. So one direction releases heat, the other direction absorbs heat, and it's the same amount either way. So carbon in the form of that is 1 mole of carbon in the form of graphite plus 1 mole of O2 in the form of a gas yields 1 mole of carbon dioxide gas. Delta H for that reaction is negative 394 kilojoules, as we've seen. If you wanted to take carbon dioxide, 1 mole that is, of carbon dioxide gas, and convert it to 1 mole of graphite and 1 mole of oxygen gas, you would have to put in 394 kilojoules of energy. Or in other words, delta H is positive 394 kilojoules. So remembering that, it should be fairly easy to come up with delta H's for reactions, even if they're not listed, even if that specific reaction is not listed in tables. Now, this reaction here should be pretty easy to find in the tables because you'll notice you're creating nitrogen dioxide gas from its constituent elements in their lowest energy natural form. And you just happen to be creating 2 moles of nitrogen dioxide gas. So you could just look up the standard enthalpy of formation for NO2 and double it, and you'd have the delta H for this reaction. But you can also do it with Hess's law. If you can find 2 reactions, like for instance, assume that for some reason we have a really crappy table and the heat of formation for NO2 is not available in that table. But we do have the delta H for this reaction. 1 mole of nitrogen plus 1 mole of oxygen forms 2 moles of nitrogen monoxide gas. We have the delta H for that, that's plus 180.5. And we have the delta H for this reaction, nitrogen monoxide plus 1/2 mole of O2 yields 1 mole of NO2 gas. And the delta H for that would be negative 57.06. So we have those 2 reactions, and the reaction we want is the one that I've drawn the box around. And the thing to do is look at what's in the target reaction, that is the reaction whose delta H you want to figure out, and look for those things in the constituent reactions or the individual reactions that you're given from the table. So we want 1 mole of N2, and we want it to be on the left-hand side, a reactant, in other words. Well, the only place N2 occurs in either of these two reactions is right there. It's on the reactant side of the first reaction that we're trying to add up to the overall reaction. It's on the correct side, and we have the correct number of moles of nitrogen. And so we're probably going to end up being able to use the first reaction as it is without changing it. The next thing we'd look for would be oxygen, O2. Now, oxygen actually occurs in both reactions. And so if something in the target reaction occurs in more than one place in the individual reactions that you're trying to get to add up, then it's best to leave that for later and hope that it works out on its own. So we'll ignore the oxygen for now. But what about NO2? Well, we want 2 moles of NO2, and we want them to be the product. The only place NO2 appears in these individual reactions would be on the product side of the second reaction. But as it's written, we only get 1 mole of NO2 out of that second reaction. We want 2. So we double the coefficients in the second reaction. That gives us 2 moles of NO2, and it also converts the 1/2 mole of O2 into 1 mole of O2, and it converts the 1 mole of NO into 2 moles of NO. But that also means that we have to multiply the delta H for that reaction by 2. So make sure you do that as soon as you make the change in the reaction. Make the same change in the delta H, otherwise you might forget. And now, if we take these two reactions and divide them at the arrow and add up everything on the left-hand side and add up everything on the right-hand side, and then consolidate things that appear on the same side, cancel out things that appear on opposite sides, what we get, first of all, is 1 mole of N2 plus 1 mole of O2 gas plus 2 moles of NO gas plus 1 mole of O2 gas yields 2 moles of NO gas plus 2 moles of NO2 gas. Notice that 2 moles of NO gas are present on both sides, so you can cancel those out. And also, you've got 1 mole of O2 gas on the left-hand side here, and 1 more mole of O2 gas on the left side there. Those can be combined into 2 moles of O2. And so what you end up with is 1 mole of N2 gas plus 2 moles of O2 gas yield 2 moles of NO2 gas. That is the reaction we wanted. And so now you just add up the delta H's, remembering the fact that you've multiplied the second one by 2, and you get plus 66.38 kilojoules, which would be the delta H for the target reaction. All right. That one was fairly simple. There is an example also, one of the ones, check your understanding examples that the book doesn't work out for you, which asks you to find delta H0, that is the standard enthalpy for the reaction 2 moles of aluminum solid plus 3 moles of chlorine gas yields 2 moles of aluminum chloride solid. All right, actually, for one thing, you'll notice that you've created a compound from its constituent elements in their lowest energy standard form. Aluminum is normally a solid at room temperature and room pressure, and chlorine comes in pairs. So Cl2 gas is the way you would normally find chlorine at normal temperatures and normal pressures, and they combine to form a compound. So actually, again, you could look up the standard enthalpy of formation for aluminum chloride and then double it, because this reaction produces 2 moles of that, and you would have your delta H. But again, assume that it's a really crappy table and we don't have heats of formation for aluminum chloride. So you can use several other reactions to figure out what the delta H is. One of these reactions is HCl gas going to HCl aqueous. That is, hydrogen chloride gas becomes hydrochloric acid. And the delta H for that is negative 74.8 kilojoules per mole. Forget what I've multiplied them by for now. And another reaction is 1 mole of hydrogen gas plus 1 mole of CO2 gas yields 2 moles of HCl gas. And one other reaction that might be interesting would be 1 mole of AlCl3 aqueous, dissolved in water, in other words, transforms into 1 mole of AlCl3 solid. Delta H for that is plus 323 kilojoules per mole. And yet another reaction that might be interesting would be 2 moles of aluminum solid plus 6 moles of aqueous hydrochloric acid yield 2 moles of aluminum chloride aqueous plus 3 moles of gaseous hydrogen. Now, actually combining all of those together, you can get this reaction here. This is our target reaction, the one that I drew the box around just now. All right, so these are the things you're looking for in the reactions down below. We want 2 aluminum solids on the left-hand side. Reaction number 5 has 2 aluminum solids on the left-hand side. And so we're probably going to be able to use reaction 5 as it is. Okay, so that's the first thing. We need 3 Cl2 gases on the left-hand side. Reaction 3 has 1 Cl2 gas on the left-hand side. So we're probably going to need to multiply that reaction by 3, which means multiplying delta H by 3 for that reaction. So that'll give us 3 Cl2s on the left-hand side. And we need 2 AlCl3 solids on the right-hand side. And let's see, we have 2 AlCl3 solids on the right-hand side right here. Or sorry, we have 1 for reaction 4, which means we're probably going to need to multiply reaction 4 by 2, which means multiplying the delta H by 2 also. And the one problem that we're going to have with this reaction is that when we add everything up, and we can do that as an intermediate step. So if we're going to take 3 times reaction 3 plus 2 times reaction 4 and 1 times reaction 5, what we're going to end up with would be, okay, so this is 3H2 plus 3Cl2 yields 6 HCl gas. 2 times reaction 4 is 2 AlCl3 aqueous, goes to 2 AlCl3 solid. And then 1 time reaction 5 would be 2 Al solid plus 6 HCl aqueous yields 2 AlCl3 aqueous plus 3H2 gas. If we divide these at the arrow and add them all up, we get 3H2 plus 3Cl2 plus 2 AlCl3 aqueous plus 2 Al solid plus 6 HCl aqueous. And on the product side, we get 6 HCl gas plus 2 AlCl3 solids plus, I'm going to run out here, 2 AlCl3 aqueous plus 3H2 gas. So we can do some canceling out here and see what we get. And we have 3 H2s on the left cancel out with 3 H2s on the right. Those Cl2s don't cancel. AlCl3 aqueous, 2 of those cancel with 2 AlCl3 aqueous on the right-hand side. 2 Al solids don't cancel out with anything. the 6HCl aqueous does not cancel out with 6HCl gas. So they would both have to stay. So we end up with 2Al solids plus 3Cl2 gases plus 6HCl aqueous yields 6HCl gas plus 2AlCl3 solids. So we're almost there. This isn't quite the reaction we wanted. Remember, the reaction we wanted was 2Al plus 3Cl2 yields 2AlCl3 solid. We've got these HCl's in here that we have to get rid of. Well, we have HCl aqueous on the left and HCl gas on the right. If you notice, the first reaction we were given was HCl gas going to HCl aqueous. Well, if we just multiply that reaction by 6 and add it to the rest, that will cancel out the two HCl gases. So if we take this times 6, this is 6 HCl gas yields 6 HCl aqueous. So if we add that in, the HCl aqueous on the left-hand side here cancels out the HCl aqueous on the product side here. And the HCl gas on the left cancels out the HCl gas on the right. So now we really do have 2Al solid plus 3Cl2 gas yields 2AlCl3 solid. So that's how we actually do it. You take the total of first reaction times 6, second reaction, or sorry, reaction number 2, the way the problem was set up. Reaction number 2 times 6, reaction number 3 times 3, reaction number 4 times 2, and reaction number 5 times 1. Make those same changes to the delta H's, add them all up, and you will get your delta H for the overall reaction, which is negative 1,407 kilojoules. Okay, so that was a little complicated. We didn't have to reverse anything, but we had to, with all those reactions, there was quite a bit to keep track of. But mainly you're just looking to find the things that are in the target reaction in the individual reactions. And if there's something that appears in more than one place in the individual reactions, then skip it and go on to the next thing. And pay special attention to phases of matter. Because remember, like in this case, we had HCl aqueous and HCl gas, and we had AlCO3 aqueous and AlCO3 solid. So if you're not paying attention to the phases of matter, that can really mess you up. Okay, and then one other thing we can do is something like this. Use delta heats of formation values. Okay, I mentioned that you can use heats of or enthalpies of formation values to find the overall enthalpy change for a reaction, and it's just products minus reactants. But I didn't actually show you how to do it until just now. So using heat of formation or enthalpies of formation values of reactants and products to find enthalpy changes for a reaction, that is actually a form of using Hess's law. Because if you basically write out all the reactions for formation of the products from their elements and formation of the reactants from their elements, and you take products minus reactants and algebraically cancel out all the stuff that's the same on both sides and add up all the things that are the same on the same sides, you end up with the overall delta H for the reaction you're trying to find the enthalpy for. So, and that's a form of Hess's law. In practice, what you need to do is take the total of the heats of formation for all of the products minus the total of the heats of formations for all of the reactants. The more mathematical way of writing it would be sigma, or the summation of N, that is number of moles, times delta H of formation for each of the products, and add them all up, minus the summation of moles, number of moles times heat of formation for all of the reactants, add them all up, and then products minus reactants will give you delta H for the entire reaction. You need to multiply each of the heats of formation by the number of moles present in the balanced reaction, because heats of formation, of course, are given in kilojoules per mole. So that's why you have to do that. So for an example, we can calculate the enthalpy of combustion of 1 mole of ethanol to form carbon dioxide gas and water liquid. Now, we looked at this value a little bit a while ago, and we recorded that the heat of combustion for ethanol was negative 1366.8 kilojoules a few pages back. So I'm writing that there just as a reference. If you look up enthalpies of formation in the tables, you'll see enthalpy of formation for ethanol is listed as minus 278 kilojoules per mole. The enthalpy of formation of H2O liquid, remember you got to pay attention to the phase, so it's H2O liquid, is negative 286 kilojoules per mole. The enthalpy of formation for carbon dioxide gas is negative 394 kilojoules per mole. And the enthalpy of formation for oxygen gas in the form of O2 is 0, because that's an element in the form that it's normally found. Our reaction is, remember from the thermochemical equations and from the heat of combustion, is 1 mole of ethanol plus 3 moles of oxygen gas will yield 2 moles of carbon dioxide gas and 3 moles of water liquid. So if we take the summation of all of the heats of formations for all of the products, and then subtract the summation of all of the heats of formation for the reactants, in practice, what that means is, remember, start with the reactant, or start with products rather, 2 moles of CO2 times minus 394 kilojoules per mole of CO2 plus 3 moles H2O times negative 286 kilojoules per mole of H2O minus, and then brackets, 1 mole of ethanol times negative 278 kilojoules per mole of ethanol plus 3 moles of O2 times 0, because the heat of formation for the element in its normal natural state is 0, and add all of this up, and subtract them, and it ends up being negative 1,646 kilojoules minus negative 278, which is the same as plus 278. And so we end up with minus 1,368 kilojoules. And that's as opposed to minus 1,366.8 or 1367 that we had before. So very close. Like I said, I mentioned before that using heats of formation gives you the approximate enthalpy change for a reaction. It may not give you the exact value, but it will be at least approximate. And in this case, it was pretty close, actually. It was only 1 kilojoule per mole off. So that's using enthalpies of formation in order to find the enthalpy of a reaction. Okay, well, we're a little over time on the second segment of this lecture, but that's all there's going to be for this lecture because we're now at the end of chapter 5. So I won't do a third segment for this lecture. We'll come back next week and start chapter 6. This also means that the homework for chapter 5 will be due next week. I'll make that due, say Wednesday next week at by midnight. So for chapter 5 homework, I'll send out an email about that also. Okay, so finally done with chapter 5. So I'll see you next week.